Well, thanks everybody for joining us. This is a good turnout. Today we're going to have two presentations about Pyregence. Is that the right pronunciation?
Correct pronunciation,
yep.
Yes.
Pyregence is a consortium that does modeling of wildfires. And part of the reason that we wanted to hear from them is because it's a big group with clusters within it. And I think we'll hear about that, about how they're organized. The group that we're all a part of as of last spring has lots of focal points within it and a fair bit of overlap, but also a lot of diversity. And I think one of the things we've been discussing is how can we use this group in some beneficial way, both professionally for us within the group, but also as a service to folks outside and to our partners in government agencies and nonprofits and industry and academia. So with that, Jean-Pierre, you want to go first?
Sure.
And so if you could just start off and introduce yourself and then take 20-25 minutes and then hand it off to Michael. We can have some questions after your initial presentation and then some additional ones after Michael's, however that works out.
Great, sounds good. So, so my name is Jean-Pierre Wack. I work at Spatial Informatics Group. We're the lead on the Pyregence Consortium, and my role is really partnerships at SIG. So I'm part of this consortium on wildfires, and I also work for a Servia Amazonia Consortium, which is a NASA USAID funded program to deliver geospatial services in the Amazon. So this sort of consortium model and how to make it work, and some of the, we've had some bumps and rides along in these various consortiums. So I'm happy to share about that and discuss in the Q&A afterwards. So kind of 2021, but 2020 was a lot of carbon emissions in California. This came out from our ARB. So the annual wildfire emissions was a quarter of economic emissions in California in 2018. So if you run the buildings for 3 years, or commercial and residential buildings for 3 years, that was equivalent to all the emissions from wildfires in 2020. Real scale. And it was a real baptism of fire for this consortium. We started in 2019, and we were sort of appointed in 2019, and this was our first fire season. So things broke, and yeah, there was a lot of work. One article I'd recommend is in the Wired magazine. They had a really nice, a lot of interviews with some of the consortium members and others, and looking in detail at the situation in 2020 and some of the wildfire science questions that were and the challenges involved. And it's a really nice narrative. It's a good article to share with individuals who aren't involved in wildfire science as well. So Pyregence, free and open access to the next generation of wildfire risk models for grid resiliency. So we received funding from the California Energy Commission with 3 goals: advance science, apply those into models, and then integrate at 2 levels, one with the utilities and the other in the sort of resilience planning, climate change, mitigation, adaptation planning. And that funding effectively acted as the seed funding for a consortium of organizations that have been working together for a long time in different situations. And so our approach to meeting those goals, we really see this value chain between science and impact. Can I just go robotic? Is the sound quality okay?
Yes.
Yes. Okay. So we get working across this value chain from science to impact, where impact is really from a California Energy Commission perspective. So this is a resilient grid that is safe and cost effective. And we work through that. We get to that impact objective through 2 levels. One is with near-term forecasting tools that are focused on the electric utilities. And then another, which is sort of climate scenarios, climate projections for the 5th climate change assessment. So this is California's sort of state-led initiative to do more sort of vulnerability assessments and adaptation planning at a state level scale. And some of the previous work that's been done by the consortium has led to wildfire impacts assessments and the climate change for the previous assessments. And then at the beginning, really, there's there's a whole set of scientific gaps in the wildfire science that we're aiming to address through two areas. One is around fire behavior, and the other is in extreme weather. So that's our approach. This is what the team, the consortium looks like. I'm not going to go into detail on specific organizations, but I do want to kind of highlight a couple of facets. So one is the interdisciplinary nature, where each of the organizations here really brings in a specific expertise, whether it's on the academic institution side or on sort of private sector organizations, technology companies, or also operational fire people with operational fire experience, like Prometheus and Deer Creek. And it's that interdisciplinary nature that's really attractive within the consortium, where different organizations interact and integrate. The second part is that this is, so there are academic institutions, federal research organizations, private sector companies, and each of those organizations have different purposes and goals, whereas UC Berkeley may have a really long history and resilience and fuel mapping and all these amazing sites where they've done great field work. Other organizations like Dave Marvin at Sailor Sciences have been around for a lesser time, but still have really excellent expertise to bring to the table. And the part I wanted to highlight around that is the different sort of approaches and horizons that people look at, and aligning incentives across those different horizons, given these different organizational structures and business models and ways of operating, is a real key part of a consortium. And we do that, we're doing that at the moment by looking at governance mechanisms. So if we are going after a commercial opportunity, or if we do see another research funding opportunity, how do we manage that in the context of a consortium? And I think that those governance mechanisms are good to be transparent about. And that's one of our ethos, is really radical transparency, is how pushing out information that's relevant and as much as possible, so that people are made aware of whatever opportunities there are or whatever other challenges there might be in the consortium. So the way we're organized, which may be of interest given your current situation, so we have 4 broad work groups. So there's these 2 work group 1 and 2, which are really focused on the advancing research, and one's led by Janice Cohen, extreme weather, and then the other fire behavior, Scott Stevens. So there's a set of organizations that work in that particular focus. And then on the tools, on the more sort of operational integration side, we have Chris Lautenberger and Leroy Westerly. And so that being able to separate into groups allows for real sort of effectively these sort of communities of practice, whatever other jargon we want to use, but real focused work on a particular topic. And then at SIG, we're responsible with an integration team formed from consortium members to kind of integrate and encourage the dialogue around key topics across those work groups. And we do that through various formats, whether it's specific meetings focus about a specific topic. We review with the technical advisory committee on a sort of 6-monthly basis, and then we have project team meetings as well. So that discussion and dialogue within the group and between the groups is really critical, and there's obviously an administrative load to having 20 partners as part of the same consortium, but that mix between the work group is really what we can do to really bring some secret sauce to the table. So the way I'm going to do the presentation, I think I'm about 10 minutes in. So I'm going to focus on the forecast tool because that was most relevant to 2020, and then I'm going to touch on the other groups just briefly, and happy to follow up with either via email or question Q&A afterwards. Okay, so let's get going. So in work group 1, this is extreme weather, and at the mesoscale, so at NCAR, Andy Prayan has been looking at extreme weather types. So he's been going through days of extreme fire growth and trying to identify from an atmospheric perspective what was the type of weather in there. And so here you have recognizable weather patterns, and also some other weather patterns like these weak gradients, which are situations that are conducive to plume-driven fires. And so we've done this typology to really identify these different extreme weather types based on historical analyses of fire data. Then at the microscale, Janice Cohen is running a Corfi model, which is a coupled fire and weather model, to look at some of these fine scale dynamics. And then with these two efforts, we're looking at trying to identify the blind spots in the current forecast models. Where are things under predicting, over predicting? And that information then is used to inform a weather station optimization for utilities. So where is there uncertainty? Where is there the most benefit to installing weather stations? And then in parallel to that, we are doing a pilot study of a SODAR equipment, which measures the vertical profile of wind. So looking at not just at wind at say 15, 25 meters, sorry, transferring from meters to feet there. It's looking at the vertical profile of wind. And this is really interesting in terms of looking at the sort of the forecast at a 5 to 10 day range as well. So that's the work group 1 part. Work group 4. So this is focused on the climate projections. There's a great website called CalAdapt in California, which hosts a variety of data on adaptation planning. The team there at JIF have taken the efforts in the 4th climate change assessment and integrated that onto that platform. So you can review some of the climate projections, wildfire impacts under those climate projections with different climate models and pathways for carbon emissions. And what we're doing in the consortium now is we're taking that approach in the 4th assessment and then elevating it by doing things at a finer resolution, integrating the WUI into that analysis and a variety of other elements. That's more a nascent stage with the products, and we're really creating the initial data lakes there. Here's a bit of a sort of spaghetti meatballs diagram of what that looks like, and I just want to highlight 2 things here. One is that we're really trying a compare and contrast approach. The issue around uncertainty of climate models is really important, and by using different landscape simulation models, different fire risk simulation models, we're hoping to see some of the differences in approaches and how that impacts our projections on wildfire risk. And then finally, there's the work group 2. So that's the real focus there is on how do we build the next generation of fire behavior models. And so there's really 3 angles. One is burning stuff, which Michael might explain about in his presentation, and then burning stuff at a small scale and a large scale, where the Missoula Fire Lab is building out a grain silo to burn logs at different ventilation rates to really look at the physics of ventilation in that space. Secondly is developing new fuel mapping systems. So Berkeley are going out and doing various analyses of the heterogeneity in fuels. So really looking at that fine scale and going out with ground-based LiDAR and really picking up, where are these logs? Where are these different, what's happening in the dust and all those different spaces. And then a third part is trying to scale that up and looking at a wall-to-wall scale, which so Dave Marvin and Salo Sciences has been looking at tree mortality. We're reviewing how that is impacting on a lifestyle and is likely to impact future fire situations as well. Okay, so the fire forecast tool. This is work group 3, and this is the sort of the baptism of fire. And I just want to highlight the team in this space. So Chris Laudenberger taking the lead. He's the originator and developer for the Wildfire model. Pyrologic, Joe Scott, and then Spatial Informatics Group, SIG, us, with Gary Johnson and Matt Spencer and Kenny. And we all work together as part of the California Public Utilities Commission fire threat maps. And so one of the things that happened there that we thought was really beneficial was Chris was developing Wildfire for these fire threat maps, and then we were developing GridFire for those fire threat maps as well. And there was this compare and contrast, and that open source model where we could say, this is the fire equation we're going to use, fire spread equation we're going to use here, or fuel model we're going to use here, have that reviewed by a scientific committee, and then come back to us and say, actually, this is maybe a better option. And that compare and contrast approach is something that we're implementing in the climate projections and also implementing here. So that, and open source is a real key part of that, so that you can be aware. Each organization can be aware of what the other is doing. if you're taking that to an extreme level, the grid fire is written in literate programming so that you can actually read the code like an academic paper. The fire spread equations are linked to this particular code block, fuel models, this particular code block, and then you compile the code from that PDF. So for someone like me that doesn't read Clojure, I can actually read the PDF, look at the academic references, see what data sets are going in, and then the code then gets run from that. So I think that idea of open source is really important, and we're really trying to implement that in a scientifically robust way. The other side to this is this modular design architecture. So we're trying to make it possible to integrate different data sets, different models, all the way throughout the workflow. And we'll go into some of the nuts and bolts on that, but that's a real key part. So we're really lucky to be able to use the CFO data. We use that alongside the Wildfire and the other fuelscapes that are around. And we want to be able to integrate best practice as we go along. The third part is scale. The compute, the 10,000 lightning strikes and 250 fires, that really busted our compute. And so although we've built a lot of the geospatial information technology to be able to scale, we just didn't quite expect that much. So that was a key learning from 2020 is, what are the limits to our scalability? And then fourth is we're a user-driven consortium. And this is a topic dear to my heart about how do you productize science? How do you get the right product market fit? What are the right characteristics? How do we take this basic and applied research and really make sure it's packaged in a way that is suitable to the users? And that key part of getting scientists talking to product marketers, product managers, is a really hard conversation at the beginning. But now that we've got into it for 18 months, that's really creating a fruitful development cycle. And that agility by reducing the time for basic and applied research to get into operational models is one of the key drivers of why we do that. Okay, so what do we do? So this is the Pyregence.org website, and it's just going to go through some of the fires that happened over the 2025 season. And so we do active fire forecasts. So you can select a fire that's based on fire locations from satellite data, and then run the forecast for that fire based on fuels and current weather. And so here, this is the marsh fire being selected as part of the lightning complexes, and you can see the fire forecast as it spreads out across the landscape. So we tried to do this for all fires CONUS-wide last season. Some of it was complicated with all the fire perimeters coming in, but the scalability of that was matched, and this was our beta year. We were in beta launch, so this year in 2021 will be in full launch. So there you go. You see the marsh fire spreading out across the landscape.
Excuse me, Jean-Pierre.
Yep.
Just a question there. So are you showing the modeled spread or the actual spread as observed?
So the actual part is those hotspot detections from remote sensing, and then everything that goes from then on is forecasted.
Okay, and one of the things we heard in the presentations about Wildfire was their ability to get a plane up over active fires so that they could then calibrate their models more effectively than had been the case in the past. And I assume you have access to that same kind of information.
Yes, and that's really important for our review of how to work on the different models. And there's various ways of changing the sensitivities to models given some of the issues around uncertainty and whether it's fuels or weather. And that data is really useful. I'm not sure if it's the FireGuard that data that Wi-Fi is using, but we're trying to ingest 15 terabytes of FireGuard data at the moment, and just starting on that.
Great, thank you.
Okay, so that's the active fire forecasts. And at a sort of high level, the way it works is we have a weather pipeline that takes in data from National Weather Service, looks at we take the fuels and topography, and the real-time location of fires, runs it through fire models. We do the spread forecast and then push that out to various users. What that looks like in the kind of nuts and bolts. So we have a variety of sources of information and model data inputs. And this really highlights this modular architecture. So on the vegetation and fuels, we have the land fire data sets and then the California Forestry Observatory fuels. On the models, we have M fire, grid fire. On the weather pipeline, at the moment, we're using the National Weather Service forecasts. So that ability to ingest different models is really important for the consortium for delivering best practice. And then we have a variety of hazard outputs, and I'm going to talk through a couple of the other products just briefly here. So the wall-to-wall products that we deliver, one is a look at impacts from wildfires to the grid. So we have an ignition density layer that looks at human-caused ignitions. We then light those fires in a stochastic way across the landscape, and then do a Monte Carlo analysis to look at where there are risks of where there is risk of fire. So this focuses in an area around Placerville. Here you see the relative burn probabilities based on current fire weather data. And you can look down into the individual properties to see, okay, you know, over the next 5 days, if a fire was to happen here, these are the types of fire sizes that we would see from 6 hours from ignitions. So this is a wall-to-wall data. This is all accessible on data.pyregence, either via GeoServer or a web API, a web application or an API. So if this data is of interest, please feel free to get in touch. The other side is on utility caused ignitions, where here we're displaying the transmission lines, and this shows the consequences of ignition on a transmission line. So if there was to be ignition in here, this is the fire size that's likely to happen. And two utilities, Pacificor and Liberties, are using this with their distribution lines, which is proprietary data, to then look at decisions around PSPS or vegetation management and grid hardening. And so this uses the same workflow with the weather pipelines and the fuels as well. We also, as part of the weather pipeline, we have a variety of indices available, and these are listed here. This is CONUS wide, so this allows us to model active fire CONUS wide. So we have a variety of some of the fire forecasts from 2020, if anyone's of interest, to see those up in Oregon and Washington State. We haven't done any in Canada. And likewise here, you can click and see at each point what is the forecast on an 8-day time series. Finally, the roadmap. So I would just want to focus on two things on the roadmap here. One is the coupled fire weather piece. So working with Janice Cohen on how do we integrate atmospheric conditions into this sort of fire weather interaction. That's something in progress. And then the post-Rothermel side is once work group 2 with UC Berkeley and Missoula Fire Lab have progressed further with their new fuel mapping systems and fire spread models, we're going to integrate that into this operational decision support system as well. So that's the Pyregence Consortium. I just want to explain a bit about SIG and some of our value proposition, and that's that we work across a variety of domains across this value chain of science, policy, and markets. We look for the gaps in research, where there are slightly perverse policy incentives and market opportunities. And we have people with niche expertise in each of these parts, and then people that interface across those three areas. And then we just push and look for ways that we can do activities that generate impact. So that's me. There's the consortium website, and I'll put my email in the chat if people want to get in touch. I'm available. Thanks very much.
That's awesome, Jean-Pierre. Really impressive. I have about 300 questions that I could ask you, but won't right now. But maybe before we switch over to Michael, could you just talk a little bit about how this got organized early on because you have this large source of funding from the state of California, which would provide some motivation for people to participate. But I would imagine just to get it organized, it's a lot of time from a lot of people. And these are people who have other jobs. And so how did it kind of emerge into this very nice coordinated way that you've presented from what I assume were a really disparate set of people and practices beforehand?
So there were groups that had worked together. So for example, the Pyrologic SIG reacts, we'd worked together. Salo had worked with some of the folks in the work group 4. So there were these pockets of organizations that had worked together. And then we were just looking, okay, so who has best practice here? All right, let's bring in that piece and that piece. And then we had I was the lead in the proposal effort. And yeah, it was a tough time, to be honest. But I think that dialogue around how what do people bring to the table, what are people comfortable in providing, and then this sort of alignment of actually, a lot of this should be public data, and you really want to get the science into the operational models. And it was such an important opportunity, and there aren't a lot of $5 million opportunities in the wildfire space. And so I think that those small teams and then that alignment on objectives was important.
Excellent. Let's open it up to other people. If you have a question, you can either put your hand up or just say something. I've muted those of you who weren't muted, so unmute. Do you, just in looking at your consortium, it's largely California. I saw there was one New Mexico name up there, but do you have interest in partnering outside of the state? I understand the applications are going to be within California, but in terms of expertise, you mentioned NCAR as another group that's outside. Could you just talk a little bit about the California focus?
Yes, so there's funding restrictions. That there's different points if you are in state or out of state. So that was one of the reasons for it to be California focused. We are working with USGS in different offices, NCAR, University of New Mexico. So we're happy to collaborate outside, but that's one of the reasons why it was California focused. The active fire forecasts are CONUS-wide, the weather pipeline's CONUS-wide. So the application of this in other states is really encouraged, and we're looking at ways of extending the hazard modeling at the moment, CONUS-wide, and hope to be able to do that in the next year. So yes, happy to collaborate.
Yeah, so I would say within this group, including several of the people who are on the call right now, there are folks who I think are complementary to the expertise that you have and would have interest in seeing some of these techniques, which are really nicely developed, extended northward. We talked about, the same thing came up when we talked about Wi-Fi and what would it take, what kind of investments would be required from the state of Oregon, the state of Washington, province of British Columbia, because it makes no sense for us to try to reinvent all the work that you guys have done or the San Diego folks have done. I think maybe we could have some follow-up conversations about that afterwards. There's also, I don't think Doug Toomey is on from University of Oregon, but so Doug runs the Alert Wildfire program out of University of Oregon, which has the camera system. And Doug is putting together a large mid-scale infrastructure proposal to NSF to look at networking across the West Coast, but focusing on Oregon for the first phase. And I think so a question that would come up for all the work that you guys are doing is, what is the networking infrastructure that you have across the state, and what would you need to make it better? Because one of the things in Oregon is there are certain areas where you might have cameras set up, but there's no way to get that data into the system very effectively.
In a previous life, I sold fire detection cameras in Indonesia and China. So I have a sort of parallel thing in there. And I think the networking opportunities, we talked with Alert Wildfire last week about how, that workflow of getting that integrated. And I think the early detection piece is really important with remote sensing and detection cameras and how to do that network spaced up. And our approach really here is this sort of modularity, just to be able to integrate the various data sets, whether it is from Alert Wildfire or from the other successful people in the RFI2. That's really our principle. So we're really open for collaboration and for others to use our data sets and to ingest other data sets as well.
Okay, and Chris, you had a question?
I did. Yeah, thank you so much, Jonathan. Yeah, it was a great presentation, Pierre, or Jean-Pierre. That was fantastic. One kind of technical question I had for you. It looked like you showed the level set method. Is that how you're tracking the fire boundary? And you also talked about the Forbes Fire Weather Index system. I'm not terribly familiar with the Forsberg Fire Weather Index system. So you guys do incorporate fuel moisture into the modeling effort?
So, so the second question's around Forsberg and fuel moisture. What was the first question again? I broke up.
Oh, I saw just a nice, partial differential of the level set method in your slide. And I was just curious if that is what you are using to track the fire boundary.
So yeah, on the remote sensing side, that's one area where we've been struggling actually, is ingesting the firm's data and the GOES and really getting those fire perimeters correct. And that's been something that we're working on for next fire season. The fuel moisture side, we use it in the energy release component that then feeds into the ignition density and that whole risk forecast piece as well. And that weather pipe comment too. Go ahead, Michael.
Yeah, I would just add that, so Chris, the fire perimeter is tracked using the level set method. The base of the model is similar to Farsight, which is the back end of Wi-Fi, but it still uses the sort of elliptical spread. The difference is with the level set method, you designate burned, and so you can have gaps. But what Jean-Pierre was referencing, I think, is there's some interesting issues that arise with the size of the cells for ignition of different resolution from GOES or VIIRS, and how many cells then are ignited on an ignition. And so there are some issues that arise there and how best to do that with differing resolutions to initiate a fire.
Thanks, Michael.
Thank you both. That was great.
Thanks, Chris. Jean-Pierre, could you just talk a little bit about how you take your information and get it to different agencies that are responsible for dealing with the fire? I mean, how is that coordinated? We have some people on the call from the BC Wildfire Service, which is largely research oriented as well as some operational things. But it would just seem like you've got this fantastic information. Lots of people would want to use it. Some of the people who need it wouldn't know how to use it. So how do you get all the people in the field to best take advantage of all the work that you're doing?
So this year was a better year, the year where we're running in better. And the way we've designed it is on 3 levels. So there's the web application, which are actually quite complicated to do, to display the scale of information in a quick, responsive way. So that's one area to access. The other side is there's a data API that you can directly connect to, or there's a geo server where you can pull from our data servers. And so that, with those 3 options, that gives enough flexibility depending on the user, on how they want to use or how they want to get to it. And so with the electric utilities, they're using that at the moment through the web application. There's a Department of Energy that's using this data for looking at in their sort of multi-hazard resilience models. They're pulling that directly from our geo servers, from the data.pyregence site. So there's a variety of ways depending on the user. Some of the data has been used in evacuation procedures, and we're working with Zonehaven on that play in terms of how to integrate that more on the sort of the user, as in really at the coalface. So there's a further layer there in terms of how to get that into the right hand.
Great, thank you, Michael. Why don't we turn to you? I think there'll be opportunities for some related questions probably after your presentation.
All right. So yeah, my name is Michael Gollner. I mentioned earlier, so I moved to UC Berkeley in January 1 year ago. So I was briefly on campus before this all hit, and I was previously a professor at the University of Maryland for 7.5 years. So my background is in combustion, fluid mechanics. So I've been more on the experimental side, and as Jessica Block from Wildfire mentioned, I was on the original proposal there. I did my PhD at UCSD and knew the group when that started. And so part of my introduction to user tools was through that. And really, I think my expertise has remained on the background end you know, we start with experiments and models and come up with the back end of how a model's going to work, come up with something usable. And then there's still a huge process to pulling the data in, putting it together and getting it used to users. Today's models, whether we talk about Pyregence, Wi-Fi, or whatever, they still rely on, you know, Rothermel's 1970s equations. And so that's one of many areas that we work to extend. I only have a few minutes, so I'm going to talk a little bit about Wildland-Urban interface, and that's really what you asked me to touch upon. I've done a lot of work on embers, which are important there, and give some background. So I think we know that there's obviously been a huge increase in the United States of area burned and fires, and that's increased the suppression costs. What you see on the left-hand side is that the number of fires in blue have almost gone down a bit, but the area burned has gone up. And if we look in California specific data, the area burned was just this dramatic doubling leap from any previous record last season. It jumps off the charts. And so obviously our suppression costs are going to be jumping there too. And suppression costs are really a small fraction of what happens. Unfortunately, you know, one of the things we look at a lot is where these fires go beyond you know, the forest, chaparral, rangeland, and move to structures in the wildland-urban interface. And we saw this now in Oregon and Washington over the past few years, particularly last year. But California has been, you know, ground zero. In 2017, there was a host, the Tubbs, the Nuns, Atlas fires, over 14 billion of losses, 22 deaths. The Camp Fire in 2018, 16 billions of losses, 85 deaths. And the number of homes consumed, you can see in Camp Fire, there are over 19,000 structures. Some fraction of that was homes. You know, the trend is going up, and I would actually say for the size of the fires last season, we were very lucky. In fact, there were a small number of structures burned compared to the area and the number of fires that we had. And so that was good in some ways, but we're still really behind in this wildland-urban interface problem. And so you can see here, this is just another California perspective, the top 20 largest California wildfires. A vast majority of them are in the last 10 years. Whether you rank it from acreage burn, structures, number of deaths, there's really been a massive increase over the last 20 years. And this is publicly available. It's probably outdated again. During the summer or October, November, it just kept updating every day. It was insane. So where do we move from, you know, we have a wildfire to we have a wildland-urban interface disaster? And so this is a PNAS paper based on a PNAS paper by Kalkin et al. And also Mark Finney and really Jack Cohen's concepts. And I think we all are aware high winds and dry fuels, especially following drought. We have high fire danger days, and we get extreme fire behavior with high fire intensity and growth rates. But what really occurs to change and move this into the wildland-urban interface is where we start having residential fires. And so, you know, if we look back into the history, the National Fire Protection Association came up with codes and standards 50s and 60s for structures in what we now call the WUI, but in the forest. They were concerned about those structures igniting the forest, and because things were pretty spread out. Now we're talking about residential structures which abut natural lands, and there's lots of them. And some of that's due to development, some of that's just due to the fact that the fire behavior is changing with climate change. But when we have multiple home ignitions, we start moving beyond what the fire service is capable and really used to responding to. And so what happens is you have a community, let's say with 1,000 homes which are exposed. Maybe only a fraction of them are actually ignited. The persons have evacuated, and now the fire service is overstretched. And when you have overwhelmed resources, they just diminish in effectiveness. And studies investigating past WUI fires in Colorado and California have shown by Marangides et al. That fire protection, you know, actually having a truck in front of the house with water is the most effective, you know, means of preventing ignition. But let's face it, in California, some of these fires are threatening tens of thousands of homes at a moment. There is absolutely no way to protect all those homes, to get the resources there in time or ensure safety. So we have to start doing things in advance, or we get this WUI fire disaster where hundreds, thousands, now tens of thousands of homes are destroyed. And I know that WUI disasters aren't only about homes, but you know, structure ignition is really the main focus we have. And you can see the effect in the Camp Fire, which was a occurred in Paradise, California, which was, in a large forested area. And Coffee Park was a community in Santa Rosa, California. This was actually not marked as a high fire danger zone. It was across the freeway and well within a suburban area. But once embers penetrated the community, the homes were very close to each other. They didn't have defensible space and just sort of fell like dominoes, you might say, under these very high wind conditions. It's also not a California only problem. I haven't updated with any Oregon slides, but Gatlinburg, Tennessee in 2016, 2,400 structures were destroyed with over 14 fatalities. And so this is and obviously a global problem. Just given the time, so I want to focus, there's two areas we talk about, and I think we've been talking about modeling wildland-fire, and that is a challenge as it is, right? We must couple data from weather, modes of heat transfer, the types of fuels, the wind and weather, there's flame dynamics, you might incorporate smoke and emissions. Something we often skip is the home ignition part. And so what we can do now, and what we do is look at the exposure to structures into the wildland-urban interface. If we move to the future, hopefully we'll change and actually start to see what is the susceptibility of different communities to these fires. And that's something where we haven't moved yet. But there is a big challenge getting to that point. And I think it's demonstrated, this is a picture of Coffee Park in Santa Rosa. You can see how the fire literally stopped on one side of the street. And there was no full investigation, but by all accounts, it does not seem that there was a large fire crew action here. It may have simply been a change in the winds or a large enough separation. Radiation would spread from home to home. You see the grass is green and things are good in some areas. But, how do you model a process that occurs like this? And so we have to start by understanding what's driving it and how we can do this. So what causes homes to ignite? And there's three main exposure conditions we look at. First, radiation, which has originally been thought of as being responsible for most or all ignitions. If you have a fire and it spreads to a home, the closer the fire is and the larger the fire is, the more radiation you're going to get to the home. This is the basis of defensible space recommendations. If fuels are moved further away from the home, a radiation will not be sufficient to ignite the exterior of the home. And somewhere between 30 to 100 feet, depending on the fuels, generally accomplishes this in just about any scenario. The other factor is something called direct flame contact, which can be some of the same thing. But if you think of smaller flames that may not be strong enough to radially ignite a home, we've now seen that fences are a direct means of igniting a home. Now, this is a fire that could be put out by a firefighter or a fire crew with a hose. But if no one's there or there's simply too many things on fire, it's easy enough for small flames to penetrate under the stucco or wherever on the exterior of the home and then ignite the whole home. The home has no applicable suppression, and even in-home sprinkler systems don't prevent exterior ignition. And so, basically once the fire penetrates a home, all bets are off, and it's usually a total loss. And finally, embers are firebrands, which based on studies are now 50 to 80% responsible for ignitions, whether it's direct or indirect. But if you have a fire, those small embers will land on materials next to the home or on the home itself and light fires. And one of the most challenging things about embers, besides it being totally stochastic for modeling, which is a great reason why we're using Wildfire, which is a stochastic model, we also now have to look at features that may ignite 9 hours after the fire front passes. You get small smoldering fires that then flare up under different wind conditions. And so ignition by firebrands is a challenge. And it is the primary mode of igniting. I think the bottom right and the top left exemplify this. These are both homes in San Diego County. And you can see how the homes literally burned out from the inside out. And is most likely an ember that penetrated somewhere within the attic and then spread along the roof and then inside without even going to the exterior of the home. And then this is just a demonstration. As always, if you take bushfires in Australia, they're always the most extreme. And so these embers just show up beautifully on video because of the bark on eucalyptus, which, if you know where I am in Berkeley, we are surrounded by eucalyptus forests that people have planted over the last 100 years. So this is a reason why there's a lot of fire danger in the hills, amongst other reasons. And so, I just want to touch on the, where do we go from here? There's a lot of processes in firebrand modeling, from how they break off, how they loft, and how far they go to spotting ignition. And, on my end as an experimentalist, there's a wide variety of research, whether, NIST, IBHS in the top right and the bottom two are some of our experiments, but looking at how embers are generated. And one of our key goals is getting these into models and understanding how structures respond to the embers that are igniting different features. And so, if we talk about modeling, I think, models don't yet move from wildland to WUI. We still need to prioritize actions, recreate events, and plan response. And there's a lot of different approaches in how we move forward. A physical modeling approach to all of this is 5 to 10 years, but risk and hazard evaluation is coming, 3 to 5 years, but even now. And what I mean by that is that we can take today and understand the exposure to structures and try to reduce that as much as possible. We can also try to harden those structures as much as possible. And so it's really on the exterior of structures, the spacing between them, and defensible space. I'm really short on time, but there is a whole host of resources, and if you want to get in touch, that are available to folks who are looking at trying to harden structures. And so what we do in a risk analysis is to then, or risk or hazard analysis, is look at both ends, look at the exposure from the wildland to the structures, and look at how those structures will respond. And there's sets of tools on both ends. WUI is not directly part of the Pyregence project today. It wasn't part of the original planning. It came from the California Energy Commission, but it is something that we're continually talking about because it's a highlight of a key issue. And we are doing other work incorporating WUI modeling just through NSF funding, looking at that. And so, eventually we need to look at these risk assessment methodologies, and that's really something that, and so in my group, myself, we've actually moved to the same platform that Pyregence is using, Wildfire, is to take from the landscape scale, which is what's being done for Forest Service and other analyses, to move to a community scale, where we look at the influence of that exposure to different structures. Risk assessment is already a mature scientific approach, but it isn't really brought down to the structure and community level. And we need to connect those conditions with structural loss. But eventually, it all comes down to this same fire triangle on the right. You take the likelihood of a fire, the intensity of the fire, and the susceptibility of whatever structure or community, and that becomes your wildfire risk. A lot of the work that I do, we do real-time fire modeling, but I like to say that we also have to think of the applications before. So I see a lot of the things that's going on with Pyregence, both, I don't think you mentioned this as much, Jean-Pierre, but in terms of fire risk forecasts. So they're getting more localized fire risk forecasts to local regions. I think that's really helpful. And I hope in the future that we'll also be able to do other things where we go to a community scale and to do comparative analyses of actions. And that's something we've been pushing and developing for some years, is how do engineers, landscape planners, foresters actually do an analysis of a community to find the best approach to minimize risk. And I think these modeling tools are going to play an important role in that. It may not use real-time data, but there's a lot of data that builds into that. So I'll leave it at that. I know the time is short, and this was originally a little bit of a longer presentation. So I'll be around for questions.
Thank you, Michael. That's really fantastic. I'll just make one general comment and then open it up to others. One of the things that's come up in the course of the webinars we've had is that Washington and Oregon in particular are becoming more and more California-like with climate change. A difference potentially is that we have these major cities west of the Cascades that have not had any kind of frequent fire risk. The repeat intervals for big fires around Seattle and Portland is hundreds of years, but that may get shorter. And these are cities and Vancouver that have a huge amount of tree cover in the city, and they go directly up to forests. I mean, I'm in Vancouver right now looking at North Vancouver, and there's just this forested mountain that comes right down to where all the houses are. So I think to look at those questions that you've been talking about in the context of the potentially higher risk in Washington and Oregon and British Columbia to what California has had might provide some nice complementarity and some justification for wanting to extend the work that you guys are doing northward. Because we're talking about things that over the next decade or two will become more and more likely. And we've seen it in Portland the last 3 years, Seattle maybe not as much. Anyway, so that was just a general thought. But this is really helpful to see your presentation. So open it up to anybody who has a question. And if nobody says anything, I've got another one. So Michael, I'm on the advisory board for KB Home in LA. So 5th largest home builder in the United States, one of the biggest ones in California. They build whole communities, and they are very open to adding new technologies into the way they build homes. Our advisory board persuaded them 10 years ago that they should start worrying about water use. And so they started doing that, and it's turned out to be really helpful for their home buyers. Similar with solar. And so to your Ember study, are there some specific things that a home builder could do that would maybe reduce the risk of ignition from embers?
Absolutely. And it's not, you know, and so this will build on your other comment. It's not just California advice. You can go to IBHS, which is an insurance consortium. It's disastersafety.org. They have some beautiful advice. UC-ANR, which I'm sure many of you are familiar with. It's the Agricultural and Natural Resources. They have this UC extension with a wonderful, Steve Quarles started it, and now there are many other colleagues who do this, and they have great advice, as well as the California, CAL FIRE has another website. There's hosts of websites which all have basically the same advice. It's very structure dependent, but that's a really good start. We have to get to the community scale, but structure-wise, we can tell you what to do. And if you imagine, you need to essentially make sure that the fire doesn't ignite the outside of the structure. And that's what we call defensible space, is moving fuels away. That doesn't mean a bare yard. Green grass, by the way, hates fire. It's almost impossible to ignite, and it catches embers, so that's great. But the 5 feet from the home, you want completely clear. And then beyond that to 30 to 100 feet, depending on surrounding fuels, you want to dramatically reduce that fuel load. And there's a lot of local guides. There are for British Columbia as well. I'm sure you can find, I don't know exactly where to find it, but I've seen presentations and resources of types of landscaping. When you get to the home, you obviously want non-flammable siding and a Class A non-flammable roof. You want to make sure that valleys and dormers and eaves are non-flammable and don't have any penetration points for embers. Just imagine, you know, that little smoldering cigarette times a million landing like hail or rain all over your house. You need to make sure that that can't start a fire. And so if it lands in an area that it can't ignite, then it won't. Mulch around the base of the home is the worst possible thing. And I've seen multiple builders continue to do that because it's simple and it's easy and it's lower water, but that's actually very bad for fire. You want to keep the fence non-flammable within 5 feet of the house. Vents need to have 1 millimeter, very small holes to prevent the embers from getting in. And they sell vents that follow current standards on that. CAL FIRE has California Building Code Chapter 7A, which goes through all of these. And then the products and materials are accepted by the state fire marshal. I want to add, you know, well, one, KB Home would be great to engage with. One of the maybe 10 to 20 top. We had an NFPA sponsored workshop in March, just before everything happened, here in San Francisco. And one of the main things that came up was engaging between construction, insurance, and real estate and getting them on board, because we're not going to be able to force everybody. And can we get Home Depot and others involved to incentivize people to make changes to their personal property and their homes to reduce fire risk? And so there's a huge human side. If we can get the builders and current homeowners on board, that would be great. But it's not just a new technology. We've worked with other developers. And they're always, well, we have this great new technology, this will solve everything. You know, I tend to think of it, there's no one vaccine pill that's going to solve this problem. It's more like, you know, heart health, eat healthy, exercise, do all this, and you're really going to reduce your risk. And so there's lots of solutions for each of those aspects, but it takes maintenance. And
excellent. Thank you. And if you would be interested in talking to our advisory board, we meet twice a year and we get speakers on topics like what you were just discussing. And so we could follow up on that afterwards.
Sure.
Again, if anybody else would like to jump in.
I got a question, John.
Good. Go ahead, Aaron. Thank you.
Yeah, Michael, you began your talk mentioning how increases in fire activity across a lot of sectors, but in particular, increasing numbers of structures are being burned in recent years. You know, so one potential window of opportunity for reducing the hazard to home ignitions is in the regulations that get put in place for rebuilding structures. Are you guys looking at any policies in particular for rebuilding in some of these communities that have been heavily impacted with lower fire ignition potential?
yeah, I mean, I'll start off. I'm in mechanical engineering, so policies are a bit beyond me. I can give a pitch that we run a California-wide, which is open to anyone. There's a lot of people who join internationally. We have 1,300 on our mailing list. It's at frg.berkeley.edu, which is Fire Research Group. So it was part of a proposal, and we've kept it going to just have a seminar series. We had some speakers talk about these policies. There's a lot of issues, and typically what I've been told, you know, learned from these speakers, is that it costs more money to rebuild, and there's nothing to force the insurance companies to pay that. And so a lot of towns have actually been super lenient to say, build it as unsafe as you want, not up to code, to make it cheaper to get people, you know, back in their homes. And it's really upsetting to us as researchers to see this, because we see them building back unsafely. And so I think it's still safer than it was, but it's not up to code. And so that's disappointing. And in Coffee Park, that community on this slide, was exactly what happened. You know, you have to remember, though, that rebuilding is such a small proportion. The fact is that most homes are already built. And that's the hardest place to make a change, is homes that are already built. As a clear example, you saw some recent fires in Southern California. Few homes burned down. They were built a couple years ago. Fuels are still clear. Stucco is fresh. People haven't modified and done things. And they were built to certain building regulations. Even if they're not perfect, it's still better than it was. So we do see, you know, older structures, and prior to the introduction of some WUI codes, being much worse off on some general anecdotal analysis. Hopefully there'll be broader analysis in the future.
Great, thanks, Michael. And your point that you're not focused on policy is well taken. It does seem like your models are a great opportunity to demonstrate the effectiveness of certain policy decisions for home ignition potential, in particular, by modeling different scenarios based on those regulations.
Yeah, and we definitely want to be more involved with that. And you know, the data that we use right now as we look at developing a WUI model, it doesn't exist. It's in, you know, something we're trying to develop. You know, we're working with CAL FIRE on that, and they're obviously incredibly interested in the analysis of the effectiveness of their codes, because if they see their methods effective, they can push lawmakers to try to enact stricter regulations. But in the end, the vast majority of structures are already built, and this is the biggest challenge area we see.
Great. Michael, I have one more question. So if we were trying to get some discussions going in Washington, Oregon, British Columbia about increased risk of WUI fires coming into the metro areas, are there some California people you would recommend that we bring in for advice and just for brainstorming?
Sure. I would say it's best by email, and let me know the topics of discussion. But you know, there's a lot of different consortiums and groups. much looser than Pyregence. I'd say, Pyregence, both because of the funding and because of people like Jean-Pierre who actually work at a company and don't also teach class and advise students and apply for. I know you do a lot, but I'm saying that there's actually some people who are staff who help manage. And so we're super annoyed that someone keeps us on track, but at the same time, it keeps us on track, And so I think that's a difference. But I work with a lot of groups, from IBHS and CalFi and others, and we host this NFPA workshop. And depending on the expertise, WUI is a small world. And whenever we work with folks, everyone always laughs because everyone has already talked to each other. There's maybe a dozen or two people who do that primarily for research. I'd love to get them, connected up there. There were a number of people, obviously, and the name is escaping me. I don't know why. The big WUI fire in northern Canada.
Yes. Right.
So, yeah.
Right. Okay. Well, that's really helpful. Anybody else who's on here? We tend to lose people at 2 o'clock, but I can stick around another couple of minutes. We had Doug Toomey was on for just a minute or two, but he may want to follow up to talk about this infrastructure issue. In your list of partners, is Nature Conservancy involved in any of your discussions? Because they're quite interested in wildfires and forest health. And so it would seem like they do have some modelers, but probably not the level of what you have.
Yeah, Jean-Pierre, do you want to?
Sorry, I was just chatting with someone on the chat box. Sorry to blank out there. So you mentioned with TNC and some of the work there. Do you know on the WUI side we haven't done much. We're working with we have worked with TNC in the past a lot around forest carbon, and we're looking at that piece, but not directly in the Pyregence consortium. I mean, Dave Marvin had done a lot of work with TNC, and some of that work is pushing through into the climate projections, but that's it on that side.
Okay, well, I think we're losing people in time. I just really want to thank both of you again. This was highly instructive, and I think it kind of points to a direction that we could potentially try to go if we could find your $5 million nest egg. But even short of that, if we could establish a little bit more dialogue between what's going on up here and what's going on in California, especially if we could find some questions up here that would be complementary to the things that you're able to do most easily in California, we'd love to pursue that. So thank you all for sticking around, and we'll see you next week for a couple more talks.
Okay.
Thank you all. That was really interesting.
Thanks. Good to meet you.